Hello friends and welcome into the lecture of digital communication. In last lecture we have covered the concept of DPSK and we have seen there that the two drawbacks for the DPSK are going to exist, in which we have commented that if one error is going to happen for a single bit in the DPSK, then that will be reflected in the next going symbol of the DPSK also. Because when the DPSK symbols are to be found, we have seen that we are going to refer every time the previous bit and the current bit in the binary bit pattern that is applied. And that's why we are moving further with the next concept of Qpsk, where from this Qpsk now we are starting with the M-array modulation schemes, which are seen as with the four number of signal levels, and that's why this will be also said to be the 4PSK modulation. Until now we have covered only two-level modulation processes, but here from after this we are starting with the different M-array level modulations. In the two-level modulation schemes, always the bit rate and the baud rate for the system was remaining constant, and whatever the maximum bit rate we are going to achieve from the binary signaling schemes, whether it was ASK, FSK or PSK, that was not meeting the requirement of any of the data communication system. And this is happening due to the problem of limited bandwidth of the telephone voice channels. And so here we have to look for the modulation schemes in which, even though we are keeping the baud rate value constant, we have to get the bit rate to be increased. And this need will be given or solved by the multi-level modulation schemes. And that's why from the two-level modulation, we are moving towards the multi-level modulation scheme, in which the baud rate of the system will be kept constant, but due to the number of bits involved in each symbol, the bitrate for that system is going to increase. So in this QPSK system, as the M value for this system will be becoming as a 4, because of that, for each of the signal to be represented, the symbol in the system will consist of the group of 2 bits. And for each of the group of bits, we will have a different phase representation associated with it. So in M-array level signal representation, generally, with each of the group of bits, a specific value of amplitude, frequency, or phase of the carrier is associated. If we are following for ASK, then different amplitudes will be represented. If we are using FSK, then different frequencies will be presented, or otherwise the different phases will be represented. So QPSK is said to be the multi-level phase modulation, in which to represent the 4 different signals, we have to have the grouping of 2 successive bits to be done. Grouping of 2 successive bits to be done. And each of that message or each of that signal will be now represented by some distinct phase shift value associated with the original carrier. So each signal is having different phase value associated with respect to its original carrier. So here we can see the demonstration for the combination of two successive bits. To accommodate all possible group combinations here, I have represented purposefully those groups as 0, 0, 0, 1, 1, 0 and 1, 1. So this above bit representation indicates the bit string in which every bit is going to exist for the bit period, which is indicated by TB. While to make a symbol or to represent individual message, we are going to group the two consecutive bits, and that's why here below we have represented 0, 0, 0, 1, 1, 0 and 1, 1, which are nothing but the symbols which are indicating the separate messages, and they will be also mentioned with the title of S1 to S4. So here each symbol or message is going to consist of 2 bits, and that's why here the symbol duration for every message is nothing but 2 dB, because every symbol consists of 2 bits. These symbols will be transmitted by transmitting the same carrier at the 4 different phases. So let's see for each of the symbol representation what is associated phase shift value and how that will be represented on the signal space diagram, which is known as constellation diagram. So here the table has been presented in which the two bit grouping combinations have been presented as 0, 0, 0, 1, 1, 0 and 1, 1. So here associated with each of the symbol, the carrier phase shifts have been indicated, which are mentioned as 0 degree, 90 degree, 180 degree and 270 degree. So if you are observing here, for two consecutive symbols, the phase shift of constant value of 90 degree that has been maintained for two consecutive symbol representation. So here you can observe that the symbols along with their amount of phase shift for the symbol representation has been given on the signal space, and that diagram is known as a constellation diagram, as it is 4 phase shift keyings. So 4 symbols 0, 0, 0, 1, 1, 0 and 1, 1 will be represented. When we are moving from this 0, 0 symbol representation towards this 0, 1, this will have 90 degree phase shift with respect to the symbol of 0, 0 presentation. If I shift from 0, 0 towards this 1, 0, this 1, 0 will have totally 180 degree phase shift with respect to this 0, 0 symbol representation, which going to indicate that 90 degree phase shift for this 0, 1 as compared to 0, 0, and again another 90 degree phase shift with respect to this 0, 1 for the 1, 0 will occur. So in short, we can say to get the symbol of 1, 1 corresponding to this 0, 0, we will have totally 270 degree phase shift that has been represented. And so in the table, we are finding that 4 different phase shifts are going to be present. So in short, this Qpsk can be indicated as a 4psk also. Now the waveforms for each of that symbol has been represented in the 4psk wave, where we can understand this is a carrier with 0 degree phase shift, while this will be with 90 degree phase shift. This will be with 180 degree phase shift from this particular signal, and this will be with 270 degree phase shift. So in this way, the 4 different symbols can be accommodated in the same modulated output representation. So here in the upper constellation diagram, we have started with coinciding with the reference lines for drawing the axis itself. But when we are starting with the 45-degree phase shift for representing the symbols at the starting with respect to the reference axis. This like representation is also possible for giving the constellation diagram of the QPSK system. But we have to remember that in these representation, when we are writing the symbols, that symbol writing should follow the gray code representation. That means the two consecutive symbols should vary in a single digit only. So with respect to that gray code mapping over here, we have to place the successive bit representation for getting the symbol to be represented. So here in the alternative representation, instead of 0-degree phase shift with respect to original carrier, we are starting with 45-degree phase shift for the original carrier. Then corresponding to that 45-degree phase shift, 90-degree will be added to that 45-degree. So it will be 135-degree. So it will be given by 3 pi by 4. Next will be 5 pi by 4 and next will be 7 pi by 4. And this is how here you are observing the first symbol that we are starting with 1 0, but to have a gray code representation, after this 1 0, I can have 1 1 or 0 0 in the representation. So I am having this 0 0 in the representation. After that, for representation in the gray code format, 0 0 will be given by 0 1 and then as 1 1. So this will be initial 45-degree phase shift. In that 45-degree phase shift, this another 90-degree will be added because in QPSK, constant phase shift addition of 90-degree is going to happen for each of the next symbol to be represented. So this 45 initial phase shift plus this 90-degree, that makes 135-degree over here, 135-degree over here plus this another 90-degree, which will give me totally 225 degrees phase shift over here, which is given by 5 pi by 4, and this last one is with 7 pi by 4. So in this way also the constellation diagram is going to be represented. So in the two different constellation diagram representation of the QPSK, we are finding that either we are starting with the coinciding with the reference axis, or we are starting the symbol representation with initial phase shift of 45-degree itself. Now we will turn towards the mathematical representation of the QPSK signal. So basically, in the mathematical representation of the QPSK, this under root 2 PS is nothing but the amplitude of the signal itself, because PS is going to indicate the symbol power value, and under root of that power means definitely it is the amplitude value, and it is multiplied with 2 because for each of the symbol we are having the 2 bits included into that, and that's why here 2 PS has been observed. Now, after this under root 2 PS cos of omega ct plus twice m plus 1 into pi by 4, that has got represented. And this particular equation we are writing for the constellation diagram representation, which is given by this alternative method, where now in the bracket this m value is going to change from 0 to 3, because we know for QPSK m value, that is multi-level signals, are 4 in number, and that's how here by changing the m value inside the bracket we can get the equation for the different symbols to be obtained in this QPSK output itself. So the symbol equation for S1 will be obtained by putting the m value at 0. So automatically if I am putting the m value equal to 0, this bracket will reduces to 1 and it will give the equation as under root 2 ps cos of omega ct plus pi by 4. If we will replace this m value with 1, then this bracket will reduces to 3. So this will become as 3 pi by 4 and this whole equation will give me the second symbol representation and so on for finding the third and fourth symbol to be obtained. Now, one another small change we can do, and that change is related to the symbol energy and the symbol time duration to be represented. Because in some of the books, inside this square root, instead of this PS, you will find E by T that is mentioned, where E is nothing but the symbol energy and T is the symbol duration. So, in some book, you will find out under root 2 E into E divided by T, which is one and the same for representing this under root 2 PS value. After observing this mathematical equation, we will turn back to the modulator and demodulator diagrams to be obtained for this Qpsk process. So in this Qpsk transmitter process, as usual, first we are going to take the binary bit sequence. But this binary bit sequence will be now converted into the bipolar data sequence. Now what is this bipolar data sequence? So if in the binary bit pattern bit value is 1, then that will be converted to some plus v value, and if binary bit value is 0, that will be converted to some minus v value. So likewise 0 and 1s will be represented as minus v and plus v representation by this NRZ level, bipolar NRZ level encoder, which is indicated by the signal BT. After that, on this BT signal, the demultiplexer will be applied. This demultiplexer will be applied for giving the separation of the bits from each other. That means the even number bits we are going to separate and the odd numbered bits also we are going to separate out. And this task is achieved with the help of the demultiplexer block. Here, if the even numbered bits we are going to separate, that will be indicated by the bit sequence of BT, and odd numbered bits are going to separated and indicated with the bit sequence of BOT. But please mind that either it is BET or BOT, for that also the symbol duration is of twice TB period. Because we know that if I am saying 0 is a first bit value, then after the first bit, second bit will present and then the third bit is going to come. That means to get the next odd bit value, I have to have the completion of first bit period as well as second bit period. That means 2 bit times has to be elapsed to get the next odd numbered value. In the same way, the first even bit value will be the second bit value. After the second bit, third bit will occur and then the fourth bit will occur. That means here to get the second even numbered bit value also, we have to have the elapsing of 2 bit period after the first even bit has got occurred. And that's why either we are following the even bit sequence or odd bit sequence, the symbol duration is going to exist with the period of 2 TB only. And we are knowing that always we are starting with the odd numbered bit value, and that's why the even bit sequence will be always started one bit period delayed with respect to the odd bit sequence, and this delay period is said to be the offset in the bit sequence starting, and that's why this Qpsk is also said to be the offset Qpsk process. Now here, after getting these two bit sequences to be separated by using the demultiplexer, we are going to multiply these individual bit sequences to the carriers of under root ps sine omega 0 t and under root ps cos of omega 0 t. Here, cos and sine, these two carrier signals are said to be the orthogonal carrier signals, and each of that bit stream is going to multiply with individual orthogonal carrier signal. So let's say that the BOT, that is odd bit stream, is going to modulate the carrier of under root ps cos of omega 0 t, and the even bit sequence is going to modulate under root ps sine of omega 0 t. And these modulators, which are nothing but the multiplier blocks, they are also said to be the balanced modulators. And these carriers are said to be the quadrature carriers. And here the modulated output at the end of these two balanced modulators will be represented respectively as SET and SOT. These SET will be nothing but multiplication resultant of BET with under root PS sine of omega 0 t, while SOT will be multiplication resultant of BOT and under root PS cos of omega 0. But here basically, these SET and SOT are nothing but the BPSK signal output. So SET represents one BPSK output and SOT represents another BPSK output. But the difference is that here each of the symbol for SET or SOT is going to have a timing of twice bit period. That means it is exactly equal to the 2 bit times. Now, the adder will add these two signals of BET and BOT multiplication, and it will give us finally the QPSK output, because already just we have said that SOT consists of two phase shifts and SET consists of two phase shifts. And when we are going to add such like two signals, we will find out totally four phase shifts into this, where SOT is nothing but multiplication resultant of odd bit sequence with cos of omega 0 t signal, and SET will be multiplication resultant of even bit sequence with this sine omega 0 t. In QPSK, any phase change, if is there, it occurs at minimum duration of TB, and because of this offset, phase shift in QPSK signal is always of pi by 2 value. So here, how from this signal of under root ps cos of omega 0 t into BET and under root ps sine of omega 0 t into BET, the four symbols will be represented that we have to see. Initially, I have told that BT will be converted into bipolar nature, and bipolar nature means either plus V or minus V. Let's consider that plus V as plus 1 and minus V as minus 1, and that's why after separation of BOT and BET from the BT itself, that BOT and BET also will possess the value as either +1 or -1. And that's why if I am going to substitute this BOT and BET as +1 or -1 at one time for each of that, then we will find out the different symbols will be represented for the signal representation. So for doing this, we are starting with marking of this original reference axis with under root ps cos of omega 0 t, while its opposite side will be represented by negative value of it. In the same way, the vertical axis downward portion we are representing with minus ps cos of plus p under root ps sine of omega 0 t, and the upper portion we are representing as minus under root ps sine of omega 0 t. Now let's say that here BOT is 1 and BET is -1. Then by substituting that value in the upper equation of Qpsk, the ST that we are going to find out is under root PS cos of omega 0 t minus under root PS sine of omega 0. While here for this symbol representation, both BOT and BET we have considered as -1, so it will be minus under root PS cos of omega 0 t minus under root PS sine of omega 0 t, and so on with the considered respective BOT and BET values. We can find out the four different symbols that has been represented. And this particular diagram is called to be the phasor diagram for the Qpsk representation. Now we will shift towards the Qpsk receiver. So every receiver, either it is binary signaling scheme or the M-array signaling scheme, we are going to look for first the coherent detection scheme, because the coherent detection scheme or synchronous detection scheme is going to give us more accurate and appropriate results. And so here for the reception operation, we are going to see the block diagram related to the synchronous detection technique. And to get the synchronous detection technique to be implemented on the receiver side, from the received signal itself, we have to get the local generation of the two carrier signals of cos of omega ct and sine of omega ct. And this task will be achieved by the carrier recovery circuit that we have seen in the general modulation block diagram process. So here you can observe the carrier recovery circuit, which will be given by three consecutive blocks that has been presented over. The first block is the power raising block, second block is the band pass filter, and the last block is the frequency division block. But if you are remembering, I have told you that the description or discrimination in these blocks will be done based on for how much M value process this demodulation is going to happen. And that's why in the binary signaling scheme, this power raising block we have mentioned as a squarer also, because there we have to raise the power by the value of 2. But here the M value for Qpsk is equal to 4, and that's why the power should be raised by the value of M, which is equal to 4. So we are saying here for the block title as raise input to the fourth power. So ST will be now converted into S raised to 4t. After that, the bandpass filter is present. But for the bandpass filter, the center frequency value depends on that M parameter. Center frequency will be always M into Fs. And that M here is 4. So the center frequency has been mentioned as 4fs. Basically, this filter is operating on the frequency parameter, and that's why here this cos of omega ct is going to get converted into cos of 4 of omega ct, because bandpass filter is centered around the center frequency of 4fs. After this, the frequency division block has to be applied. And for the frequency division block, divide by m block that we have to implement. And m value is 4. So divide by 4 frequency division that we have to apply over. After doing this, we have to apply the two multiplier blocks in parallel to get the next processing to be done. So these three consecutive blocks of raising power value, bandpass filter and the frequency divider will give us the locally generation of the carrier from this received ST signal. And the locally generated carriers are cos of omega ct and sine of omega ct. So these carrier signals will be individually applied to these two separate multipliers. And along with these two separate multipliers, the same received signal has been applied to these multiplier blocks. Now, we are observing that after these multipliers, the integrator blocks are present. But if you are observing, for the integration, the timing or the limits that has been applied are different one. For the upper integrator, the limit applied is from 2k minus 1 TB to 2k plus 1 TB, which is of totally 2 TB duration itself. While for the lower integrator, the limits are 2k TB up to 2k plus 2 TB. Again, the limit for this application is of twice TB itself. And here, either of this integrator will be applied with the 2 TB period, because we know that whether we are having BOT or BET to be obtained, its symbol duration is of 2 TB period. And we know that for the kth instance I am considering the output to be obtained, then I have to consider 2k minus 1 TB up to 2k TB as a kth instance. Then 2k TB to 2k plus 1 TB, and from 2k plus 1 TB to 2k plus 2 TB, the another bits will be present. So here we are knowing that from k minus 1 to k, we are having the odd bit value. Then from k to k plus 1, even bit value. And from k plus 1 to k plus 2, again the next odd bit value, and so on. Likewise, it is going to happen. But for having a symbol period of either odd numbered symbol or even numbered symbol, one bit period is going to get overlapped. That means here the symbol period from k to k plus 1 is overlapped with the symbol period which is given for the another symbol which is represented in the second block. So here we are saying that the upper integrator is going to give the result of under root PS TB into BET, while the lower integrator is going to give the result as under root PS TB BOT. Now after this, the sampler has been applied, which is going to get the switching of this position to happen out after every 2 TB period. And this is how From this BET and BOT again, the BT is going to be recovered. So this is the way how the recovery of the original bit pattern is going to happen. And that's why we are saying now in the next part to comment on the required bandwidth of the QPSK as compared to the BPSK. So the bandwidth of the QPSK is always half as compared to the bandwidth of BPSK, because we have said that we are keeping the baud rate constant, but the number of bits that we are going to transmit will be more in number. And here, as we are transmitting 2 bits per symbol, and because of that, as compared to BPSK, in QPSK the bandwidth will get reduced by half. And this is what the advantage of any multi-level modulation, that the required bandwidth is going to get reduced. Now we will turn toward the advantages of the QPSK process. So in QPSK processes, as this is related to the phase shift operation, so the noise immunity is very good. Then the baud rate is half the bitrate value. That means it is more effective for having the utilization of the channel bandwidth to be done. And low error probability is going to happen. Due to these advantages, the QPSK is used for very high bit rate data to be transmitted. And the disadvantage for this QPSK is its generation and detection both are the complex processes. So friends, I think you have understood the concept of the QPSK. So today we will stop over here.